Okay, we'll begin this session with a talk on opera by Alessandro Paoloni.
Thank you. Opera is a collaboration made by 140 physicists and 28 institutions, and today I will report about the present status of the analysis of our data. As you know, the Opera project was designed to verify the muon into tau neutrino oscillation at the atmospheric scale through the tau neutrino appearance. Here you can find the very well-known chronohistory of the project. You see that the CERN Neutrino to Gran Sasso run ended at the end of 2012, and the new entry is the start of the decommissioning of the experiment at the beginning of this year, which is going ahead in parallel with the analysis of the last Opera bricks. We have to observe the tau, and therefore we have to reconcile the needs for a large mass, which is typical of a neutrino detector, and an extreme granularity to reach a micron space resolution, because we want to reconstruct the tau decay which happens at the energies of the beam in paths of the order of 1 millimeter. And we therefore use the emulsion cloud chamber technique, and the core of the experiment is the brick. One brick is made by 57 nuclear emulsion films alternated to 56 lead plates. And here you can see what actually we are looking for. A tau decay may happen as an apparent kink of a charged particle if the tau decays after the lead plating which has been produced, or a particle with a high impact parameter with respect to the primary vertices if the tau decays within the lead plate where it has been produced by neutrino interaction. The Opera experiment is quite a peculiar one because we have huge electronics detectors which are complemented by several ancillary facilities for the emulsion, the brick manipulator system for the extraction, X-ray marking facilities, development chain of the emulsion, and scanning of the developed emulsions. Few words about the CERN Neutrino to Gran Sasso beam. The detector is located at 730 kilometer distance from the beam in the Gran Sasso underground laboratory. The mean energy of the neutrinos of the beam was around 17 GeV, which is quite a high energy if you consider that the oscillation peak is 1.5 GeV. But this energy was especially optimized in order to produce and detect tau leptons. We had the contamination of electron neutrino in terms of interaction of 1% and of muon antineutrinos of 2%, with a negligible component of tau neutrinos, well, negligible means order 10 to minus 6. We collected 1.8 times 10 to the 20 proton on target, corresponding to an expected number of 20,000 muon neutrino interaction, and on top of this we have to work on an expected number of 66 tau neutrinos, but we have to correct for the detection efficiency. This is the history of the runs of the CNGS with the integrated proton on target and the evolution of the mass of the detector, because since we were extracting bricks during the runs of our experiment, our mass were variable, starting from 1.25 kiloton, corresponding to 150,000 bricks, and ending with a mass which was something of the order of 10% lower. I will recall you how we look for the taus. We start from the electronics detector, which reconstruct the neutrino event, and then they select a brick where to look for taus. We have brick finding algorithms, and they have typically 1 centimeter resolution in position and 20 milliradians in slope. And then we have to confirm the presence of an event in one brick by looking at the changeable sheet emulsions, which are a doublet or nuclear emulsions, which are placed upstream of the brick in order to confirm the presence of the neutrino interaction in the brick, in order not to decrease too much our mass during the run when the brick funding algorithm is not choosing the right bricks. We plan to scan up to 4 bricks ranked in probability for each event. But the present status of the analysis, actually we are still considering 2 bricks. And here you can find the distribution of the probability for the most probable brick by the brick funding algorithm and by the second most probable brick. And you see a decent agreement with Monte Carlo. When we have a confirmation in the changeable sheets, we go looking for the event inside the brick, and we follow inside the brick these tracks until a stopping point is found. Here we do a volume scan around this point by scanning about 1 square centimeter for 15 emulsion films, and we perform a vertex reconstruction and we look for decay topologies. And here you can find 2 examples of the agreement between Data and Monte Carlo for the reconstructed impact parameter for muon neutrino charger current interaction and of the location efficiency versus the visible energy in the electronics detector for events with 1 muon reconstructed in the electronics detector and for events without a muon reconstructed in the electronics detector. So you see again a nice agreement, and the location efficiency around 70% for events with 1 muon and lower for events without muons. We have a control sample of how we describe the procedures with of our detectors, and this control sample are the charm events, because charmed hadrons are produced in muon neutrino charger current interactions and have a decay topology which is similar to one of the taus. And here I show you the results that we have published about the analysis of the data sample from 2008 or 2010, and you can see that we are in agreement both as a total, both for the total yield of the charm and also for the distribution of the kinematical variables which we use for the analysis. Then we go ahead looking for the taus. Besides the vertex reconstruction and the decay topology reconstruction, the bricks permit also to measure the momentum of charged particles through the multiple Coulomb scattering in the LED, and also to measure the energy of electromagnetic showers, and also to perform electron gamma separation. These are nuclear emulsion techniques typical. Therefore, we can do also, and we do, a kinematical cut analysis in order to increase the signal to background ratio. I will not enter for question of time into the detail of the analysis, but this is more or less the analysis that was published in the proposal. Therefore, it's not a blind analysis, but it is somewhat similar to a blind analysis. Then, for the candidate events, we perform the track follow-down procedure, which means that we are going to develop part of the bricks which are after the brick with the event, and we follow each track in the following bricks until this track stops. This is important to enhance the muon identification up to 95%. Without this procedure, it would have been 95%. And also to improve the muon-hadron discrimination through the range measurement and the nuclear interaction detection of the hadrons. Just a brief recall of our candidates. We have observed 4 candidates. The first one was a candidate for a decay into a rho and a tau neutrino, which is the most probable decay channel. The second was an hadronic, again, tau decay in 3 hadrons, when the decay was happening in the plastic base of one emulsion film. The third one was a candidate for a tau to muon decay, so it's the only leptonic decay that we have observed, and the charge of the muon produced in the decay has been precisely measured by our magnetic spectrometer. And this is the first time that the lepton charge is measured in an appearance event. And then the last candidate, which is again an hadronic one-prong decay. You can see the tau and the daughter. The key point on this event is that this track, which is a track produced in the primary neutrino vertex, is actually classified as an hadron because of its range. Before going to summarize the mainstream analysis of our experiment, I would like to recall you which are the main backgrounds that we have for the analysis. The charmed hadrons production, they are produced typically in association with a lepton in the primary vertex. So their background is the primary vertex is not identified. This is the importance of having a very high muon identification efficiency. And we simulate with the Monte Carlo tuned down chorus data, and this is strongly reduced by the track follow down and by looking for tracks at large angle in the vertexes. Hadronic reinteraction, these are estimated by Fluka simulation validated with pion test beam data, which is reduced by looking for large angle tracks with scanning and looking for nuclear fragment search in the vertexes. And then the large angle muon scattering, this is the main background for the muonic decay channel. And we are improving the estimation of this background by taking precise lead from factor parameterization from the literature. And we are testing this with the scattering measurement found in literature, but also with the dedicated test beam whose data analysis is in progress. So, the summary. The analysis shown here corresponds to about 70% of the total sample of opera. It comprehends the analysis of the first and the second most probable brick in the events from 2008 to 2009, and of the first brick from the 2010 to 2012 data. The analysis is in progress, and update will be shown in the summer conferences, which will cover about 80% of the sample at that time. As I said, we have observed 4 tau leptons, 3 in the hadronic channel and 1 in the muon channel, with an expected signal of 2.11 taus for this value of the delta m square atmospheric, around 2.32. That was new. Now it's already increased in the new PDG version. And then we have a total background of 0.23 events. So we have an average signal to background ratio of 10, but of course there are cleaner channels like the tau to mu and noisier channels like the tau to 3 hadrons. Anyway, with 0.23 background events, we can range out the non-oscillation hypothesis to 4.2 sigmas. We have also used the number of taus observed to derive a limit, to make a measurement of the delta m square atmospheric. Then we also profited of the counting of our observed taus to put limits on sterile neutrino. So in particular, you find here the probability estimated for having 2 oscillation amplitudes, the standard atmospheric one plus the exotic one due to the presence of the sterile neutrino. We can distinguish 3 terms: the standard oscillation probability at the atmospheric delta m square, a similar term but this time with the exotic delta m square, and then the interference term of the 2 amplitudes. The neat result is that because of this interference term, you may have more or even less tau produced with respect to the standard three-neutrino framework. We have to represent our results, we have defined an effective mixing angle, sine square of 2 theta mu tau, which is given by 4 times the product of the square modulus of the new mixing matrix elements, and we are given our result in a two-dimensional space with this effective mixing angle versus the delta m square for 1. In this, we can compare our results with Chorus and Nomad, which were also looking for tau appearance at short baseline at CERN, because they were mostly sensible only to this term, and therefore you see that we go 2 order of magnitudes lower in the exclusion region in the delta m square. We have also made the special analysis for the T+1 model for high delta m square for 1 values, and we have put a limit on sine square of 2 theta mu tau at 0.116 and 90% confidence level. This limit has been translated into the matrix element space, and you can see our limit here. I have no update for the analysis of the muon neutrino into electron neutrino oscillation. The analysis is still based on 208 plus 209 data, about 30% of the final sample. We have observed 19 electron neutrino candidates, which are perfectly consistent with the prompt electron neutrino contamination of the beam. But anyway, we have put limits both on the θ13 angle of the 3 standard neutrinos. I know that other experiments now are measuring it very precisely, and also we made an effective two-flavor oscillation parameterization of the oscillation formula, and we obtain a limit on an eventual new mixing angle. Opera is also, the deepest magnetic spectrometer among the cosmic ray experiments, and this permits us to measure few things like the muon charge ratio to the highest energy up to date, and we have extended the measurement of the muon charge ratio up to energies of the order of 10-20 TeV for the muon. So this is the energy of the muon before entering the rock, the energy of the production in the atmosphere by interaction of primary cosmic rays. And you can see different models, but what we can say that up to the energies where we have arrived, this ratio is perfectly consistent with the pure pion-kaon model. We see no significant contribution from the prompt component and also from charm production in the atmosphere. And this is also a test of the validity of the Feynman scaling up to the fragmentation, in the fragmentation region up to 20 TeV for the muon energy, corresponding to about 200 TeV for the proton and neutron energy. So I have come to the conclusion. Opera has integrated 1.8 times 10 to the 20 proton on target from San Neutrino to Gran Sasso from 208 to 2012. We have 4 tau neutrino candidates observed with 0.23 event background. This permits to exclude the non-oscillation hypothesis at 4.2 sigmas. But we want to exploit our full potential, physics potential, and therefore we are doing analysis also on the muon to electron neutrino analysis, and also we are looking for sterile neutrinos in our data. And we perform also cosmic ray physics analysis, and we have published the muon charge ratio in the highest energy region up to date. On conclusion, I would like to invite you to visit the posters made by our young researchers, and in particular you will have a poster by Matteo Tenti on the sterile neutrino analysis, where you can find more details, a poster by Marco Roda on a peculiar rare physics event observed by our experiment. Then you will have also a poster on the muon tracking system by Benjamin Butner and on the energy measurement of the electromagnetic showers in the bricks for the detection of tau to electron decay channels by Bezzardo Segni. Then I stop here.
Thank you. Any questions or comments?
Can you say more about this rare event observed in opera?
In principle, I can, but I don't know if I can spoil the poster by. Well, okay, it's an event where we have two decay prongs in the same event. So, in principle, it must be charm anti-charm production in a neutral current, or it might be a tau charm produced in the same event. I mean, a charm produced by the scattering of a tau neutrinos into a tau. The point is to distinguish between the two kind of signals and to state clearly that it is a tau or not. Another thing that it is important to say anyway, if you are looking about the fifth taus of opera, that if you are thinking this, you don't have to take into account this the number of the expected taus and the expected background, because this topology is not included in this analysis, so it is not present in these estimations.
Any other questions or comments?
So, did you finish taking data as of 2012?
Yes, we have finished taking data on the electronics detector, but we are still analyzing the bricks. For instance, we have still to look for the events in the third and in the fourth probability ranked brick, when we have not found the event in the first two bricks predicted by the brick finding algorithm. So, in a certain sense, we are still taking data. On the emulsion, we are still taking data, even if the decommissioning of this huge detector is proceeding.
Any other questions? If not, thank you once more.
Thank you.
The next speaker will be Claudio Montanari on Icarus.
Sure. Okay. So let me mirror out this. So first of all, let me thank you, the organizers, for having invited me here. And the presentation is where? Okay. Okay, so I will present the status of the Icarus, now to become the Icarus WR104 program. Of course, I'm doing this presentation on behalf of the Icarus WR104 collaboration, which consists of about 60 researchers from 16 institutions. So let me start with some foreword. In 2013, we completed a long duration run of a T600 detector in Gran Sasso, in the Hall B underground. It was a very successful run. It lasted more than 3 years, and we collected data from the CERN to Gran Sasso neutrino beam and from atmospheric events. Then we stopped the run and we started the decommissioning of the detector, which is presently moved to CERN. So it is mainly thanks to the continuing effort of ICARUS collaboration and to the support of INFN that the liquid argon TPC technology has become a fully mature technology. The T600, with about 500 tons of sensitive mass, is the largest full-scale detector ever built, and is at present the only one come into operation. Microboon is about to start, but not yet. Tomorrow you will hear from Mazzonesi about the efforts that the neutrino community is doing to produce full-scale prototypes of liquid argon detectors in view of the LBNF, non-baseline neutrino facility. But the T600 exists. It's a very well understood device, and it works extremely well. Already in 2009, we proposed as a continuation of the life of the T600, a highly sensitive search for new mutant new V oscillations. It's a search for sterile neutrinos that was mainly based on the signals, on the hint that we are receiving from LS&D, from the reactors and others. So we proposed the search at the time on a neutrino beam from the PS to be built with 2 detectors. One is a near detector, which is providing a reference spectrum and composition on the beam, and the second one in a far location that is providing the eventual signal of an oscillation, especially in appearance mode. So this was done by choosing the appropriate L over E as a function of the hints that we are receiving, by using the liquid argon TPC to provide the composition and the spectrum with a high resolution, and we were planning to go to very high rates thanks to the large masses that we are capable to deploy, and with a clean beam with well-known initial composition in terms of nu E and nu mus. So about 1.5 years ago, CERN clarified the neutrino strategies, which means that CERN is providing full support to the European community on neutrinos, but this support is not including a neutrino source. And the community was invited and is invited to use neutrino sources coming from elsewhere, either in US or in Japan, for long baseline neutrino searches. So we moved our proposal to Fermilab, and we submitted a proposal at the end of 2013 to Fermilab. And then another proposal was submitted at the same time from the US groups. So we were invited to join and to merge. And so there is at the moment a joint effort which is composed by ICARUS, LAR1 and D, which is providing a near detector and the existing microboom detector, that is taking place to develop this international program at Fermilab with these 3 detectors, the near one at about 150 meters, microboom is 470 meters from the source, the far one is ICARUS, and we are using both the Fermilab booster neutrino beam and the NUMI beam that will be seen off axis with a large content of electroneutrinos at the relevant energy for the long baseline project. So we submitted at the beginning of this year, let's say about a bit more than 1 month ago, a conceptual design report for this experiment, for this project, to the Fermilab Program Advisory Committee, and we got approved at level 1, which means that we can go further on as Icarus W1-104, because we are funded for what we are going to do, while LAR1ND is going further on with a complete technical design report to be done by April this year. So here is Icarus in Gran Sasso. It's composed by 2 identical modules. Each one has a volume of about a bit less of 300 cubic meters with a full active mass of a bit less than 500 tons. We have, in each module, you see the content on the right side. We have 2 wire chambers, a plane in the middle. We have a maximum drift of 1.5 meters. We have about 12,000 wires in each chambers, and we have 4 of them for a total of about 54,000 wires with a pitch of 3 millimeters. The space resolution of this object is about 1 cubic millimeter per point. It's fully sensitive, completely homogeneous. We have also photo tubes that read out the scintillation light that is occurring in liquid argon. They are sensitive to vacuum ultraviolet light with a wavelength shifter, and they are used in this case in Gran Sasso for triggering, to provide a coincidence trigger with a charge deposition or the neutrino spill. One of the key features of the liquid argon TPC technologies is that you need a highly purified liquid argon, which means that the content of electronegative impurities has to be at the level of 0.1 ppb. I recall you that commercial liquid argon comes typically at the ppm level, so we have to increase the purity by 4 the magnitudes or more. You see our results in Gran Sasso. We had so-called steady-state conditions with at least of the order of a bit less than 10 milliseconds lifetime. This corresponds to, let's say, in the range of 0.01 ppb in argon, a factor 10 better than others. And then we changed the pump in the last period of the run, and we went to something like 16 milliseconds. That opens up the way for very long drift times in liquid argon. So this is the demonstration of how well you can purify liquid argon with the methodologies that we developed along the years. We got also a longer lifetime in the laboratory with a smaller TPC that was about 20 milliseconds. So these are the basic performances of the liquid argon. We have a very high detector lifetime. The detector is continuously on. The off time is for some electronics stop because typically of power cuts, but the detector is always on. Recirculation is continuous. It's always cold. We never had to take off a gram of liquid argon from the detector in more than 3 years. And these are the basic properties. It's a tracking device. It allows a 3-dimensional reconstruction of the events inside. It's an excellent calorimeter by the combination of visualization and the intrinsic properties of liquid argon. We have these numbers for low energy electron is 11%, a constant of 2%. we have 3% of root of E for electromagnetic showers, and we can also have a very good hadron calorimetry because of visualization. We can compensate by reconstructing the events. It's also a very good local calorimeter. We measure the energy at each point of the tracks with this resolution of a millimeter, and so we can measure the dE over dx. We can reconstruct, identify particles by the index of versus range. We can tell if we have a minimum ionizing particle or two, and so we can provide electron to gamma separation to a very high level of precision. And thanks to the resolution, we can measure the momentum for non-contained muons by multiple scattering. We achieved a resolution of 16% in the end, just below 5 GeV. That is our control samples, because in this energy range we have muons that stop inside the detector, and so we can measure the momentum by range and energy deposition too. So this is the example how we measure muon momentum. We segment the track and we compute the average scattering angle for a number of segments. We have this control sample, which is about 1,000 muons coming from the beam that are stopping into the detector, and we control, so we have a control sample, and this is the kind of resolution that we got on muon momentum by multiple scattering by comparing the reconstructed momentum from multiple scattering and the reconstructed one from calorimetry. This is another example how we do electron gamma separation. You see the distribution of the energy deposition on single wires for 1 minimum ionizing particles and for 2 minimum ionizing particles. So we can tell if this shower is initiated by an electron or by a gamma with a high degree of confidence. You see the distribution for a gamma compared from Monte Carlo expectation from single point energy measurement. So we can reject most of the pi zeros that are coming into the detector and perform a very efficient search for electron neutrinos. So this is another example. This is an electron shower. You see the density of tracks that you have there, the density of energy, and you see that the beginning of a track, this is initiated by an electron. So, and you see the showering developing along the direction of the shower. And we can tell that this is definitively an electron and not somehow hidden up by zero. So with these methods, we performed a search for electron neutrino appearance in the CNGS neutrino beam. We compared our findings with the intrinsic contamination of the beam, which is about 1%. And we got a null result, so we were capable to put the limit that you see there. There is another one coming from Opera that is more or less similar to ours, and this allowed us to exclude a large fraction of the region allowed by LSND and others. And you see the surviving spot, which is where we have to search for eventual sterile neutrinos, but this time with a short baseline neutrino experiment. So this one, you know, we have three kinds of anomalies that are coming from different experiments. Why one is coming from a reactor experiment, one is coming from Mega Curie calibration sources. This is Galax, of course. And the third one is the one of LSNB, which appears to be the most significant. So with this kind of events, we point to a region where to search for stellar neutrinos, and then, as also we learned yesterday, we have somehow to take into account what is coming from cosmology, which is telling us that the sum of the masses of all the neutrinos is even lower than that value. So we have to, this is indicated a region in delta M square, which is below the one indicated by the three objects that you have above. So now I'm coming to the future. So this is our proposal. We are going to have these three detectors. One is close by, so it's the reference one. It's about 82 tons of active mass. Then we have microboon, which is located at 470 meters from the target, and it's about 90 tons sensitive. And then we have the Icarus at about 600 meters. So in absence of anomalies, the spectrum of detected and the composition from the three detectors should be more or less identical, except from geometry. Otherwise, we should see some signal, which is, we will see if we believe LSND, it will be an electron-neutrino appearance that could be somehow reduced by some disappearance in the intrinsic electron-neutrinos from the beam. So we can overcome this by modifying the beam optics, but also we can somehow confirm or disconfirm this by looking at muon neutrino disappearance if we believe in electron and muon neutrino universality. So this is the landscape of the experiment, the three detectors at different distances along the beam line. We have another beam line which is coming from the right side, which is the NUMI neutrino beam, is 100 meters below surface. So we see also neutrinos coming from there, but off axis. And this is the potential reach of this experiment. You see for a particular case the spectra and the composition seen by the three detectors, and the coming up of a signal along the way is not absent in the near detector. There is a little bit in microboon, and then we have the T600. So with these three detectors, we could, let's say, cover the allowed region from the other experiments to 5 sigmas, assuming the efficiency and the fiducial volume cuts that we have done. This is what happens in disappearance mode for muon neutrinos at the three locations. You see again the near detector is flat, the intermediate one starts seeing something, and the far detector sees a significant deviation. For this particular choice of distances, okay, we are limited to relatively large delta M squared. You see the exclusion limits that we can achieve. And this is somehow, if we go to smaller delta M squared, what happens is that this difference, this disappearing, is vanishing. You have here an example for delta M squared, which is 0.44, which is large compared to the numbers that are coming from cosmology. And the effect for this value is limited to the lower energy beams, and is almost invisible here. But if you go farther away, we are planning or we are thinking to a second phase of the experiment with an additional stage at 12.5 kilometers, then the effect is very well measurable. So we are going to face a new situation for what we are concerned. We have a detector living at surface, so we are going to deal with cosmic muons. We expect about 11 tracks per still, and this is one of the events that we recorded in Pavia in 2001. We were at surface, and this is we've simulated a neutrino event inside, so we have to deal with this situation. And this is going to be tough. So we need to mitigate this background. We are having essentially three ways to mitigate this background. One is increasing the efficiency and the functionality of the internal light collection system. We are going to adopt a muon tagging system which is outside the detector that will tag muons coming from outside, and we are going to exploit the bunch beam structure of the beam to reduce at least by another factor of 4 the contamination coming from cosmic muons. So all these mitigations were inside our computation that were in the proposal and were used to achieve, to display our sensitivity reach. And so we started this operation of making this new experiment. We have been approved as WR104 at CERN to make the necessary changes to the T600 in order to operate it again at Ferromira in 2 years from now. And so we moved the T600 from Gran Sasso to CERN. Now it's in CERN. And there we are going to make a set of operations. We need new cold vessels for the liquid argon containment. We need to refurbish the cryogenics. We are going to upgrade the light collection system. We will show you. We are going to have a new insulation layer. We are going to change to modify a little bit the cathode planes. And in parallel, we are going to build this muon tagging system and to develop all the tools for data analysis and automatic event reconstruction, which is needed for short baseline operations. So you see a little bit of pictures of this moving. Here is in CERN. This is the new insulation that we are going to build. I don't want to go into these technical details here. The new light collection system is we are going to have a very dense PMTs deployment that is going to not only to provide the very accurate determination of the time, okay, but also the position online of the event occurring there. We are going to change the electronics. The T600 electronics is rather old. It was built 10 years ago. So we have a new version of the electronics, and we are considering to place part of it also in the liquid itself. Here is the picture of the new electronics. We came from the left to the right, so from, I think, 2 meters height to a small box sitting on the flange. So let me conclude. We concluded our long run in Gran Sasso about 2 years ago. It was a very successful run, and we achieved very good scientific and technical results there. The T600 detector has been taken from Gran Sasso to CERN last year and is undergoing a number of overhauling operations, and we expect to move it to start moving it from CERN to Fermi next year, second half, and to be ready for data taking by the end of 2017. The aim of the new experiment is to clarify the LSNE hints in terms of sterile oscillation to sterile neutrinos by new appearance. And we are planning also a second phase of the experiment to extend our sensitivity for new disappearance. So thank you for your attention.
Thank you. Any questions? If not, thank you again.
Thank you.
Our next speaker will be Marco Martini on models of neutrino cross-sections. Is your talk on?
Yeah. Okay, so I will present an overview on theoretical models calculating neutrino nucleus cross-section. Why the knowledge of a neutrino nucleus cross-section is important in connection with the neutrino oscillation physics. First, neutrino oscillation experiments require the determination of the neutrino energy which enters the expression of the oscillation probability. Then modern neutrino oscillation experiments use nuclear targets, hence nuclear effects play a crucial role. So, for example, in this new appearance result of mini-boon or T2K, you can observe that the data are given in terms of the reconstructed neutrino energy. This is reconstructed through the quasi-elastic events. You can also observe that there is an important neutral current by zero production background. So let me stress some crucial points. First, neutrino beams are not monochromatic, different with respect to electron beams. They span a wide range of energies. The neutrino energy, as I said, is reconstructed from the final state of the reaction, typically for charge current quasi-elastic events. We have different reaction mechanisms which contribute to the cross-section in the model experiment. So, for example, at the neutrino energy of around 1 GeV, the energy of mini-BOO and T2Ks, the open channels are the quasi-elastic, incoherent pion production, coherent pion production, and two nuclear knockouts related to two particle-to-hole excitations. These different processes are entangled. And now let me show some formula for the neutrino nucleus cross-section, starting from the weak Lagrangian in terms of the leptonic and hadronic current. One can express the cross-section as a product of the leptonic tensor and hadronic tensor, hence we have the cross-section in terms of the response function. Let me show you here a simplified expression which is useful for illustration. You can recognize the different kinematical terms related to the leptonic tensor, and then the hadronic part. In the hadronic part, we have the different form factors, electric, magnetic, axial, related to nucleon properties, and the nuclear response function, isovector, isospin, spin longitudinal, and isospin, spin transverse. All the nuclear dynamics information is contained in this nuclear response function. Now, concerning the form factors, they are usually given in terms of standard dipole parameterization. Now, for example, for the axial form factor, the world average value of the axial mass is this one, around 1.03 GeV, deduced from neutrino, deuterium, charge current, quasi-axis scattering, and from pion electron production. But now, let me introduce the so-called axial mass puzzle related to the measurement of mini-BOO of charge current quasi-elastic cross-section on carbon. As you can observe, a comparison between the mini-BOO experimental result with a prediction based on relativistic Fermi gas using the standard value of the axial mass reveals a discrepancy. In the relativistic Fermi gas model, an axial mass of 1.35 GeV is needed to account for data. The introduction of more realistic nuclear models, like a spectral function, random phase approximation, relativistic mean field, and so on, does not alter this conclusion. So apparently there was a puzzle, but we propose an explanation of this puzzle, which is already anticipated here by the orange dashed line. It is related to the definition of quasi-elastic. In fact, if just the muon is detected, one needs to consider not only genuine quasi-elastic events, but also events where the W boson is absorbed by a pair of correlated nucleons, leading to two-particle two-hole excitation. There is the possibility also of three-particle three-hole excitation, so n-particle and hole excitation. So, and we have shown that adding to the genuine quasi-elastic this multinuclear emission channel, we obtain an agreement with mini-boom without increasing the value of the axial mass. So as we stressed, it is important to distinguish between a genuine quasi-elastic measurement, if the muon and struck proton are detected, or a quasi-elastic-like measurement. This is the case of Cherenkov detector, like mini-boom, if just the muon is detected. In this case, one needs to include also the multinuclear emission channel. Now, these results are given as a function of the neutrino energy, so a reconstructed energy, so they are model dependent. But the mini-boom collaboration presents also the result of the flux-integrated double differential cross-section function of two measured variables, muon kinetic energy and the scattering angle. So we have compared our calculation with this experimental result, and also in this case we obtain an agreement with mini-boom, adding to the genuine quasi-elastic this multinuclear emission channel contribution. Similar conclusion have been obtained also by Nieves and collaborator. Now the mini-boom collaboration published also the anti-neutrino charge current quasi-elastic scattering results, and also in this case similar agreement in our model and similar conclusion. So the crucial role of the multinuclear emission channel. Now this multinuclear emission channel, or NPMH or 2P2H excitation, has attracted a lot of interest in the last years. There is a general agreement in the community that the inclusion of this channel is the natural explanation of the so-called axial mass puzzle. In fact, this channel was not included in the generator used for the analysis of the neutrino cross-section experiment. This is the reason of the increasing value of the axial mass. Today, there is an effort to include this channel in several Monte Carlo. And now let me stress an important point. Several theoretical calculations agree on the crucial role of this channel in order to explain the data, but there are some differences on the result obtained in this channel, as you can observe in this figure by comparing the result obtained in our approach in the one of Nieves and collaborator for quasi-elastic plus multinucleon, or just the multinucleon in the two approaches, more or less factor 2. So in the following, I will focus essentially on this multinuclear emission channel. Now the theoretical calculation of this channel for the contribution to the neutrino nuclear cross-section are essentially performed by three groups. There are the calculation of our group, sometimes called the Lyon group, then the calculation of Nieves and collaborator, the Valencia group, and the calculation in the superscaling approach of Amar and collaborator. Now, as you can observe, there are a lot of recent papers on this subject. We have also the theoretical calculation of a two-body contribution to some rules and a response in the electroweak sector in an ab initio many-body approach of Lovato and collaborator. And multinuclear excitations are taken into account in an effective way also in the Guibert transport code and in the so-called transverse enhancement model. So let me present some theoretical details. Now, as I say, the neutrino nuclear cross-section are given in terms of the nuclear response function. Here you have the diagrammatic representation of the different response in the different channels. So, genuine quasi-elastic, one particle, one hole excitation, one pion production, and here you have two different examples of Feynman diagram representing two different mechanisms leading to two-particle twirl excitation. One is related to the non-pionic decay of the delta inside the nuclear medium. The other is related to initial state nucleon-nucleon correlation. These responses are treated in random phase approximation in our approach and the one of Nieves and collaborator. Let me show you an example of nuclear response, transfer response in electron scattering for fixed value of the transfer momentum Q as a function of the transferred energy omega. You can recognize the quasi-elastic contribution, the quasi-elastic peak, the tails of the pion production, and the multinucleon contribution. You can observe that the multinucleon contribution creates a high energy tail in the nuclear response above the quasi-elastic peak. So let's go to the two-particle twirl sector. Here you have three equivalent representations of the same process. You can express it in terms of two-body current, two-particle twirl matrix element, or two-particle twirl response. Performing a cut in the final state, we have two particles and two holes. Now, some diagrams in terms of two-body current. We have the nucleon-nucleon correlation contribution and the meson exchange current contribution, pion in flight, contact, and delta term. In terms of the responses, we have the nucleon-nucleon correlation contribution, meson exchange current contribution, and the interference between the correlation and meson exchange current. So a lot of Feynman diagrams to be computed. So which are the main difficulties in this two-particle twirl sector? So the starting point is two-particle twirl hadronic tensor. You can observe that it is a 12-dimensional integral. Now, take into account the energy and the momentum conservation, we have 7-dimensional integrals, but of thousands of terms. Another problem is that we have a huge number of diagrams and terms which contribute to this channel. In some contribution, there are some divergences. And then another important point is that one needs to perform calculation for all the kinematics compatible with the experimental neutrino flux, not just only for a fixed kinematics like in the case of electron scattering. So these calculations are computing very demanding, so different groups perform different approximations in order to include this channel, that at the end, different approximation means different final results. As you can observe here, by comparing the results obtained in the approaches of the three different groups for neutrinos and antineutrino. I will come back later on the comparison on these results, but let me discuss the neutrino versus antineutrino interaction, which is important also in connection of CP violation effects. In fact, detection of an asymmetry between neutrino and antineutrino oscillation rates would be an evidence of CP violation. But nuclear effects generate an additional asymmetry which is unrelated to CP violation and which has to be fully mastered. This asymmetry is related to this vector axial interference term. So the neutrino and antineutrino cross-section differ by the sign of this term, plus for neutrino, minus for antineutrino. And due to the presence of this term, the relative weight of the different nuclear response function is different for neutrinos and antineutrinos. As a consequence, also the relative role of two-particle twirl contribution is different for neutrinos and antineutrinos, depending on the way they enter in the different nuclear responses. And so where these two-particle twirl contribution enter in the different approaches. I have underlined with different color and style the response where these two-particle twirl contribution enter in the different approaches. You can observe that there are some differences. Let me mention an example of difference. In the case of Amaro and collaborator, there are no two-particle twirl excitation in the axial part, and there are no contribution in this vector axial interference term. And this is the reason why, in the case of Amaro and collaborator, the relative role of two-particle twirl contribution meson exchange current is larger for antineutrino with respect to the neutrino case, while in our case, the relative role is larger for neutrino with respect to antineutrino, even if it remains important also for antineutrino. In the case of Nieves and collaborator, the relative role is more or less the same. So, the reason of this main difference is related to the presence or not of two particle dual contribution in this vector axial interference term. And so we have or not this contribution in this term. So in order to answer to this question, we have recently considered the difference between neutrino and antineutrino mini-Boon quasi-elastic-like cross-section. Now, in principle, the difference between neutrino and antineutrino cross-section gives only the vector axial interference term for identical neutrino-antineutrino flux. The problem is that the neutrino and the antineutrino mini-Boon flux are not identical. In any case, one can investigate if this vector axial interference term remains dominant even with two different flux. In order to investigate this point, we have introduced a mean flux, so the sum of neutrino and antineutrino flux divided by 2, and we have calculated the difference between neutrino and antineutrino cross-section using the real neutrino and antineutrino flux or the same mean flux. In green, you can observe that the mean flux contribution is dominant in the difference. It means that the interference is dominant in the difference, and so the vector axial interference term is experimentally accessible in the mini-Boon data. So we have calculated this cross-section in our approach, and we have compared with the mini-Boon data, and as you can observe, in order to reproduce this data, one needs the multinuclear component in this vector axial interference term, as it is in our case. So these results are supported also by other theoretical ab initio calculation of Lovato and collaborator, not on a cross-section, but on two different integrals of the nuclear response, so the Euclidean response and the sum rule. You can observe that in this quantity there is an important two-particle dual contribution, so these are related to the vector axial interference term. Now, some comments on this theoretical approach. The main advantage is that it is an ab initio approach, so without any free parameters. It represents the state-of-the-art description of nuclear ground state and correlation. The main limitation is that an evaluation of carbon-12 responses and neutrino carbon-12 cross-section is beyond the present computational capabilities using this approach. But the results obtained with this approach offer a benchmark for other and more phenomenological methods. So we have seen an example of an important message one can deduce from this kind of theoretical calculation. Let me show you another example. It's related to the transverse contribution to the response and to the cross-section. So as you can observe, there are important two-particle dual contribution not only in the vector contribution of the transverse response as expected from the electron scattering result, but also in the axial part, as it is also in our case. Now let's go beyond the mini-Boon quasi-elastic, so other channels and other experiments. Let's start with the T2K flux integrated inclusive double differential cross-section on carbon. So this measurement is important. The inclusive cross-section is less affected by background subtraction with respect to the exclusive cross-section. And here you have a comparison between the experimental T2K results and our theoretical calculations. So as you can observe, in order to reproduce the experimental results, one needs to consider not only the genuine quasi-elastic events and one pion production, but also the multinuclear emission channel. So these results are interesting, are important. They represent the first successful test of the necessity of the multinuclear emission channel in another experiment, in an experiment with another neutrino flux with respect to the one of mini-Boon. And now let's go to another experiment at higher energies, so the Minerva experiment, charge current quasi-elastic Q-square distributions for neutrino and antineutrino, so experimental results given in this figure compared with Monte Carlo, and here compared with theoretical calculations of Gran, Nieves, and collaborator, neutrino, antineutrino, Measures, Amaro, and collaborator. So the message is that the Minerva Q-square distributions can be reproduced also without the inclusion of the multinuclear emission channel. This is not the case of the mini-boom Q-square distribution, as you can observe in this feature where the results obtained in our approach, in the approach of Measures and Amaro, are shown for neutrino and antineutrino. Now let's move to the one-pion production sector. Let me mention the so-called one-pion production controversies. So the best theories, like the Valencia calculation or the Gibu calculation, which consider delta medium effects and pion rescattering, do not agree with the mini-boom pion kinetic energy spectrum. So mini-boom data seems to prefer calculation without final state interaction for the pion. But we know that final state interaction for the pion are important. So let me show you also recent Minerva results in the same channel. So mini-boom and Minerva results compared also with theoretical calculation and Monte Carlo. So general comment, theoretical calculation and Monte Carlo underestimate the mini-boom data, while they overestimate the Minerva one. So there is the agreement in the shape seems to be better in the case of Minerva, so some apparent tension. But let me just remind that the mini-boom and Minerva flux are different, so different energy. So let's go to the coherent pion production. Now K2K and Shibun did not observe coherent pion production at neutrino energy around the GeV, so the upper limit of K2K and Shibun. Recently, Minerva and Argonaut see evidence of charge current coherent pion production. In the case of Minerva, they see evidence also between 1.5 and 2 GeV. So some problem in the 1 GeV region. In this connection, let me mention also another puzzle. So there is one order of magnitude of difference between the theoretical calculation and the experimental results for the ratio between the charge current, coherent pion production, and neutral current. Now, before to conclude, let me discuss a little bit the neutrino energy reconstruction problems in connection to the neutrino oscillation physics. As I said at the beginning, neutrino oscillation experiments require the determination of the neutrino energy, which enter the expression of the oscillation probability. This energy is unknown. We know only broad fluxes. So the determination of the neutrino energy is done through charge current quasi-elastic event. So neutrino interact with the nucleus, the charged lepton is detected, and the neutrino energy is reconstructed via two-body kinematics. Now, the identification between the reconstructed value of the neutrino energy and the true neutrino energy is exact only for scattering with free nucleon at rest. But we know that we have a scattering with nucleons inside nuclei. The nuclear effects are important. So what is the link between the results given in terms of the reconstructed neutrino energy and the results in terms of the true neutrino energy? So in order to answer to this question, we have introduced a quantity, directly nu bar, which corresponds to the product of the cross-section times the flux, but in terms of the reconstructed neutrino energy. It is an integral of a probability energy distribution, so depending on the true neutrino energy and the reconstructed one. The main ingredient to obtain this quantity are the neutrino nucleus double differential cross-section. Okay, and here I show you an example of this probability energy distribution for three fixed values of true neutrino energy as a function of the reconstructed neutrino energy. You can observe that these distributions are not symmetrical around the value of the true neutrino energy. There is a low energy tail, which is given by the multinuclear emission channel contribution, which play a crucial role. Similar results have been obtained also by Nieves, Sanchez and collaborator, and by Lala Kulic, Moser and collaborators. And now let's go to the neutrino oscillation. For example, the new appearance result of T2K. In this figure you have the experimental results given in terms of the reconstructed energy and our theoretical calculation in terms of the true neutrino energy, the dashed line, or in terms of the reconstructed neutrino energy, take into account the energy reconstruction correction. You can observe that the reconstruction correction tends to make events like outside the high flux region, especially toward low energy side. Let's go to the new mu disappearance of T2K. So a comparison between the result before oscillation near detector and after oscillation at far detector, taking or not into account this energy reconstruction correction. So the result with the energy reconstruction correction are the one with the continuum line. So you can observe that taking into account the energy reconstruction correction at near detector, we have a clear low energy enhancement. At the far detector, we have a low energy tail, and the middle hole is largely filled. These effects are largely due to the multinuclear emission channel contribution. So as a consequence, also the ratio between the oscillated and unoscillated result will be affected by the energy reconstruction, taking into account this multinuclear emission channel. But in this context, let me mention a very recent result, a very recent T2K experimental analysis. So the conclusion of this analysis is that for the present exposure, the effect can be ignored, but future analysis will need to incorporate these multinuclear effects in their model of neutrino-nucleus interaction. And so to summarize, as I showed you, several theoretical calculations agree on the crucial role of the multinuclear emission channel, which was not included in all the Monte Carlo. So crucial role to explain the mini-Boone data, and the inclusion of this channel represents the solution of the so-called axial mass phases. There are some differences on the way to treat this multinuclear emission channel, which are reflected in the comparison with mini-Boone neutrino and antineutrino data. The nuclear effects generate an asymmetry between neutrino and antineutrino interaction. This is important for the investigation of CP violation effect. Now, the inclusion of the multinuclear emission channels is to be needed in order to reproduce the T2K inclusive cross-section. The role of this channel in the Minerva is less evident. There are some controversies and passes in the 1-pion production channel. And finally, the neutrino energy reconstruction and the neutrino oscillation analysis are affected by this multinuclear emission channel. Thank you for your attention.
Thank you, Marco. Questions? Yeah.
Your point about multi-particle, multi-hole correlations is very well taken. However, in this light nuclei, especially carbon-12, alpha particle correlations are the dominant one, which are 4-particle, 4-hole correlations. Can you include those? Because they are really important. All the models you have described fail to describe the structure of carbon-12, in particular the so-called Hoyle state at 6 MeV, which is a 4-particle, 4-hole. So that's one.
For 4-particle, for the moment, 4-particle excitation are not taken into account. In our model, and also in the case of Nieves, there are some contribution of 3-particle, 3-hole excitation, but which are related to the non-pionic decay of the delta inside the nuclear medium. But yes, at this energy, I think that calculation in order to take into account 4-particle, 4-hole excitation, this energy for the moment are beyond the present computational capabilities, except one perform a very strong assumption in order to oversimplify yes.
And also the Argonaut experiment has on argon 40 shows a large cross-section of 2 protons coming back to back.
Yeah.
Can you explain that?
Yes, I have Yes. Here I have an example of Argonaut result. So you can recognize the muon track, and then there are two proton tracks in two different situations. So this situation is supposed to be related to back-to-back particle in the initial center of mass frame, and this kind of excitation are related to initial strongly correlated pairs, while this kind of results seems to be more related to the correlation due to the Mason exchange current. So the role of the virtual excitation of delta.
Can I make just a small comment? In many of your plots, you show the experimental results whose cross-sections are basically very highly correlated, the uncertainties point to point, and you can tell that very clearly by the fact that they are all laying along a very smooth line. When comparing to theoretical curves, I mean, I know that's what experiments give you, but they give a very deceiving picture when you look at them, because it looks as if one model fits perfectly and the other is 10 sigma away, while it's only 1 sigma away, because you can shift the whole curve. That's my whole point. I mean, it's that's to be said when one shows this kind of plots.
Yes.
Sometimes the differences are not so big as they appear. Yeah.
Of course.
Any other comments or questions? Not, thank you. The last speaker for this session will be Kevin McFarland on experimental cross-sections.
So it's either a very exciting opportunity for all of you or a very boring opportunity that we have a theoretical talk followed by an experimental talk on a subject where theory and experiment are so interrelated that Marco has already shown you all the data almost that I have to show you in the talk. But I think there's still some value to this. Whenever I teach a course to undergraduates, I always tell them that it's very important for you to go also talk to other students in the course about the material, so that you can hear another language or talking about the same material. I won't, in this case, tell you who is the teacher and who is the student, but I will tell you that the language will probably be different. So, with that, I think Marco has already done an excellent job of convincing you that neutrino interactions are not simple in the nucleus, and also motivating the use of neutrino oscillations, so I will skip that. But I do want to make a point about the role of near detectors. As an experimentalist, of course, I'm very, the question that you would ask is, do all these issues with neutrino interactions go away when you have a near detector in an oscillation experiment? And unfortunately, the answer is that the near detector is very helpful, but the near detector does not make many of the problems go away. So typically what an experiment does when you do a neutrino oscillation experiment is you measure a rate in your near detector, but you have large uncertainties in both the flux and the neutrino interaction. So they become correlated by the near detector, but all the uncertainties do not go away. And there are limitations even to this part of the technique. The near detector and the far detector always see a different spectrum, if for no other reason than that the muon neutrinos, for example, have oscillated away to a large extent at the far detector. And it's also true that effects of the type that Marco was mentioning at the end of his talk, energy reconstruction biases, are the same in the near and the far detector, right? But that doesn't mean that measuring it in the near detector tells you anything about exactly what that energy bias is when you try to apply it to an oscillation formula. So whatever you do, you're relying on models of neutrino interactions driven by data, of course, in order to do your experiments. There are some applications other than accelerated neutrino oscillation experiments that I want to mention briefly to this field. So one of them is that, in fact, there's a very large background to supersymmetric proton decay modes like proton decay plus neutrino that come from atmospheric interactions of atmospheric neutrinos. So for example, in the super K detector, if all that's produced in an atmospheric neutrino interaction is kaon and other particles below Cherenkov threshold, all you would see would be the same as your proton decay signature, simply the decay products of the kaon, in this case a muon in the final state. And so you need some knowledge of exactly what those backgrounds are from the interactions of atmospheric neutrinos. Pingu has problems very much like the accelerator oscillation experiments, but in many ways they're quite a bit worse, right? Because the detector capabilities certainly are much less than, for example, a large liquid argon TPC that's being proposed for the future experiments at Fermilab. And lepton backgrounds can be a real problem in this type of detector because you simply don't have as many handles as you do even in a water Cherenkov detector. So single energetic pions, for example, like the ones you would get from coherent scattering, are a major problem in those experiments. So what is it that we want to learn by making measurements of interactions as opposed to trying to calculate them? So I sort of think of the problem as factorizable, although rigidly it's not true. It's factorizable into two problems. So one of which is what's the probability of creating a certain set of particles from the neutrino interaction? For example, in this reaction, what's the probability of creating this delta plus plus that decays to a proton and pion? And then the second problem you're worried about is what's the probability that the pion emerges from the nucleus once you've created it? And what energy and what direction will it have? Because those things will be altered by the rescattering of the pion inside the dense nuclear medium. So to put that in a language that we all understand, having spent a few days in Venice, let's think about it as what's the probability of depositing a tourist somewhere in Venice, and what's the probability that that tourist actually emerges instead of getting lost in some dead-end alley before getting to their destination, right? I thought it was funny, okay. So one thing that is important because of this issue of final state interactions is that leptons play a very special role. And they play a special role for a number of reasons, but primarily it's because they're not subject to the difficulties of the hadronic final state. One thing that Marco may not have emphasized as clearly as I will as an experimentalist is that the calculations, even the very, very difficult ones that his group and others are doing now, don't tell you everything that you need to know about the hadronic system. They're focusing on calculating what happens to the leptonic side, and that is the most important for the oscillation experiment. So some detectors only, for example, detect the lepton and infer neutrino energies for that point. But even if that's not true, you can do a much better and more reliable job of modeling the lepton. The other thing Marco emphasized correctly, I think, is that model-independent data is very important. We need data sets that can be compared robustly to different theoretical calculations. But that when you do that, it's very difficult then to go to the quantities that you would like from the point of view of understanding neutrino interactions. So here's an example. Marco showed you this data set from the double differential charge current quasi-elastic from Miniboon. So you can take one bin of muon energy and muon angle, and if you were scattering off of free nucleons, that would uniquely tell you the energy of the neutrino and the form momentum exchange in the interaction, the q squared. But adding the effects of the mean field of the nucleus already makes that a mess and broadens that out. And when you add the possibility of inelastic background reactions or multinucleon effects, that complicates the picture even further. So the model itself that you want to test tells you the relationship between what you want to measure and the energy of the neutrino and how much momentum was exchanged. And that's a real problem for our business, and it actually makes it very hard to compare different experiments. Last comment about measurements. So what's in a final state? So liquid argon has fantastic capabilities for measuring the final state, as we've heard. And in fact, so you can look at events. This is Argonude, a small test experiment that ran in NUMMI that has some very nice results. And here are events of a muon with a single proton, muon with multiple protons. But one of the things that you would like to be able to do to meet your physics goals is to be able to cleanly resolve whether this event has two protons because two protons were given a large amount of momentum transfer inside the nucleus itself, or whether or not this event has two protons because one proton careened against another proton inside the nucleus and gave you two in the final state. Is it a final state interaction, or is it something that's related to the initial state? And it's often very hard to figure out ways to tell. So always in this business, we're looking at models that don't necessarily capture all the details, and we're comparing those models to the data sets we have and trying to improve the models. The entire story that Marco told you about the 2p2h contributions to the quasi-elastic events is an excellent example of this. Clear discrepancies in the data driving improvements in the model, and that very long and impressive list of publications from multiple groups that Marco showed you. I want to make a last point, which perhaps is clear, but if you're not in this business, maybe it's not as clear as it could be. So one of the things that happens is that different neutrino oscillation experiments have very different ways of treating the cross-sections themselves and the uncertainties in those cross-sections, because they start off from a different generator, for example, make different assumptions along the way, incorporate different data sets in making the constraints. And so experiments are sort of individually going through this space. And I think one thing that needs to happen as we move into a precision era of neutrino oscillations is that some sort of global generator effort where all these different efforts by experiments to do this, learn from each other and incorporate the best practices, needs to be brought into a single tool that all experimentalists can use. And that's what the Genie collaboration, for example, would like to provide and is trying to do right now. The other problem is models themselves, even very good ones like the ones that Marco told you about, don't always get into the generators in a timely way. And there are many reasons for that. It's not easy to incorporate these models often because they are quite complicated. But the other thing is that a lot of these models aren't ready to be used by generators. They don't tell you, for example, all the details of the final state. They might just tell you about what happens to the lepton, but your detector, you may care what happens to the hadrons. And so that's always a major issue in the field. So I want to talk briefly about the different experiments in generalities. We have a lot of experiments right now that are measuring neutrino interactions in the field. And in fact, almost every result I will tell you about is new since the last time this conference was held. So why is this such a vibrant field? Well, there are a couple of reasons, but one of them simply is that when you build an oscillation experiment, almost certainly you also have built a neutrino interaction experiment, because you've built a near detector that has very high statistics and will try to reconstruct these neutrino interactions as part of the science program for doing neutrino oscillations. So we have experiments with near detectors, either identical or not to the far detector, and we have dedicated experiments, in fact, also, which have very significantly enhanced detectors that were put there for the purpose of understanding neutrino interactions. And so you have a wide variety of detector techniques, ranging from Cherenkov type detectors that are fairly close to the source, to coarsely segmented scintillator, to sampling calorimeters, and then you have very fine grained detectors like Nomad or T2K's detector, where there are magnetic fields with tracking detectors interspersed with thin targets, and various fine grained detectors either made of scintillator like Minerva or a liquid argon TPC like in this case Microboon. So a good feature of these detectors, many of these have much finer granularity and therefore lower thresholds than oscillation experiments do. The scintillator trackers and, of course, the liquid argon TPCs both. And then sort of hybrid detectors that try to have magnetic fields and tracking in order to do particle identification that way. But we also have learned a lot from the Mini-Boon experiment, which after all isn't a tracking detector really at all. It's a Cherenkov sphere. And one of its advantages is its 4-pi acceptance. So it can identify all the particles in the final state much better than a conventional fixed target geometry like experiment. One thing that's useful, and I'll talk about this a little later, is having multiple nuclei in your experiment. And finally, Marco talked a little bit about the different beams. There is really no such thing as a monochromatic beam, although if I have time, I'll come back to an idea. But having beams that are wideband and narrowband and beams of different energies is very important for making progress in this field. So the first thing I want to talk about is to amplify a few points from a data-driven perspective regarding the quasi-elastic interactions that Marco told you about. So the quasi-elastic reaction really is an ideal initial state probe in many ways, and it's been used for that for many years. So what you're doing, of course, is you're looking at a charge current reaction in this case, and nucleons being ejected from the nucleus, one leading nucleon presumably, but perhaps multiple nucleons. If this were a free neutron target, you would know the form factors, or a free proton target, you would know the form factors very well. And Marco made that point. These have been measured in multiple experiments. The problem is when you use a realistic target for a neutrino experiment, you have nuclear effects that you don't understand. So these have been studied for a long time. This is actually very old data taken by a group led by the person who's the current United States Secretary of Energy, Ernie Moniz. But anyway, and what they're doing is they're looking at the energy loss in electron scattering, and this broadening of the elastic peak that you see here is due to nuclear effects, something that can be modeled fairly well by the mean field. And then this part here is actually due to the sort of correlated pair phenomena that Marco told you about in his talk, which were not well modeled by the models at the time. So we're trying to do the same thing in neutrino physics now. So there are many measurements of nu CCQE in part, neutrino CCQE, in part because it's a reaction that every experiment, regardless of energy, has access to. So I can't talk about all of these experiments, but I want to choose a few highlights. And I'll start with one that Marco brought up, but he focused on what's going on at the very lowest energies, and then came back to Minerva at the end. So this is the problem that he mentioned. The red model is the mean field model, and when Minnie Boone first ran and didn't have access to a multi-nucleon model, they tried attempts to fix up the mean field model by artificially modifying the axial mass. And we now know today, of course, that's probably not the right solution. But there is still this nagging high energy data from the NOMAD experiment, which is, as far as we know, still valid, a very different measurement technique. And it's looking from energies from about 5 GeV on, but you see it's actually in quite good agreement with this mean field model. In other words, it appears not to demand this multi-nucleon component. So the T2K data, this is recent data from T2K, superimposed on this plot. You can see here shown in the black, has very large error bars. If anything, it probably is a little closer to favoring the Minnie Boone data, but clearly that's an effort that needs more statistics. But the Minerva results, if you look at them, Minerva is a higher energy scintillator tracker experiment. So here are antineutrino and neutrino results. These are shown as a function of q squared here, but the Minerva data is averaging over a flux, which sits in this region on this plot. And if you compare their red model, which is very similar to the red model here, what you see is that, in fact, they don't demand a significant increase. Now, Tommaso's point about the correlated uncertainties is very correct. Okay? Each of these data sets has something like a 10% correlated uncertainty that's driven primarily by the neutrino flux. Okay? So if you look at these discrepancies, you know, there may be of order 20%, and maybe this isn't so much to worry about because you're talking about 2 experiments with 10% uncertainties. And perhaps, in fact, that's the answer to what's going on. Minnie Boone may have the answer right, and these experiments, NOMAD and Minerva, happen to have fluctuated a bit low. It's possible. But I would disagree, one of the few times I would disagree with Marco's comments, by the way. I would disagree with Marco's assertion that there has been no other evidence that we need enhancements beyond the mean field picture. And I think one of them is the observation of the q-squared distribution. So if you look at the q-squared distribution in quasi-elastic scattering, this is for Minnie Boone data, this is for Minerva data. In both data sets, what you see is that the sort of mean field models slapped on top of what we know about all the form factors of the nucleon don't do a good job describing that. So here you see that because this axial mass parameter that Marco mentioned has to be pushed up to values which simply aren't physical. In other words, you have to enhance the cross-section at high Q squared. You can see that somewhat more directly in the Minerva data through its shape. So this is the neutrino data. There's a very similar, in fact, somewhat more significant picture in the antineutrino data. So what's shown here is the ratio to a generator, again, just done by putting a mean field model on top of what we know about the form factors. That's the curve shown in the blue, or similar models here in the solid red or the gray. But the best fit, actually, to this comes from something which has a multinucleon-like model. This is this transverse enhancement model that Marco mentioned. Has a little bit better fit here by accommodating some of this slope and then some of the downturn at high Q squared. So it's quite probable that the experiments through their Q squared distribution have seen evidence for the multinucleon effects. I want to talk a little more about nucleons in the final state in these measurements before I go on. Both Argonaut and Minerva, because of their ability to do fine sampling of the reactions, have produced measurements in a series of them. So here's a measurement from Minerva where we've measured exclusive muon plus proton final state. And what's shown here is a sample of such an event. So the muon is going off at a very large angle. The proton actually rescatters in the detector, but is fully tracked. And so here is the distribution where Q squared is now measured from the energy of the proton recoil. So it's a different measurement of the momentum transfer. And there's an interesting thing that's seen. The data is actually in quite good agreement with the mean field model, but not in particularly good agreement with the models that include the effect of the multinucleons. So our interpretation of this, because we see one thing when we measure Q squared from the muon scattering angle, another thing when we measure Q squared from directly probing the recoil, is that it's not clear that we have a good model for the hadronic final state, because that's the difference, right? This is being measured from the hadronic final state. The previous measurement was from the leptonic side. And so quite likely it's a deficiency of that model. Marco also mentioned the results from Argonaut, but I'll first start with Minerva's evidence from multinucleons. So what's shown here is the energy that's deposited near the vertex of a charge current quasi-elastic candidate event. And you see that there's very poor agreement between the data and the simulation and the neutrino, but good agreement in antineutrino. In our interpretation of that, this is one plot from a fairly detailed analysis, our interpretation of that is that there are extra protons in the final state which aren't being modeled, which we can take as some direct evidence of a deficiency perhaps in the multinucleon model, perhaps some close coupling of neutrons and protons in the initial state. Argonaut also, as was pointed out, has a similar measurement of multiproton events. And in fact, well, I'll go to this one. So what's shown here is the momentum of the second proton versus the cosine of the angle between the protons. They see some turn up here as you go to very backward angles. In other words, a tendency for these hammer-like events that Marco attributed to meson exchange currents. And probably this would be very hard to generate by purely final state interactions, that you get back-to-back protons being emitted. So I think what we're seeing are interesting hints, maybe not definitive measurements of multinucleons in the final state, and more data would be very welcome. So I want to move on to several other reactions. One of them is pion production. So Marco talked quite a bit about this. My perspective as an experimentalist is what we're really measuring when we measure pion production primarily is what's going on in the final state. Again, this is a case where the initial state creation of something like a delta is actually fairly well measured on experiments using deuterium, for example, as a target, old experiments. But what we don't understand very well is what happens with the fate of that pion as it goes through a carbon or, God forbid, an argon nucleus, right, and tries to get out into the final state. One of the most sensitive probes we have of that, is the energy of the pion. Okay? So what's shown here, layered on top of different pion fates, whether the pion in red interacts inelastically or whether in blue it's non-interacting, is a distribution of the expected energies of the pions. And you can see the Minerva data tends to agree pretty well. If anything, favors a little bit of an excess more towards the inelastic side. And that's seen in two channels, both the charged pion measurement, but also a neutral pion final state. And both have very similar tendencies just a little bit of a desire for an excess at low pion energies. But as Marco pointed out, this is a very different picture than somehow what Mini-Boon has seen. So that picture is different both in the overall rate of the pions, but also in the shape. You notice that if anything, Mini-Boon prefers a much harder spectrum of the pions. And I think the answer is right now that we don't, as Marco implied, understand this at all. Okay? If you try to form something like a ratio of the two measurements, and this is a paper written by Jan Sobczak and his student, so he looked at the ratio of the two measurements. That's shown here as a function of pion kinetic energy. You see that the ratio is near 1 and then turns up at very low energies if you take Minerva divided by Mini-Boon. And so, as I argued, Minerva likes lower pion energies. But if you try to look at the predictions of an experimental, of a generator, and then all the possible variations that he could think of, there's really almost nothing that would alter this ratio in the current models. So this remains a real puzzle as to what could be going on here. And perhaps is somewhat problematic for the oscillation experiments when they try to form their predictions. I mentioned the need to measure kaon production as a background to proton decay experiment. And this is something that we're actively working on right now in Minerva, and T2K is also interested in doing this measurement. The signature in Minerva is kind of cute. It's actually the fact that the proton, in this case, the kaon in this case, shown as this track, stops. The colors here indicate the time of the hits in the scintillator. And then there's a delayed track shown here. That's the muon from the kaon decay. So the kaon stops, takes a 12 nanosecond lifetime, and goes on its merry way. And so by doing a time separation, you can actually get a very clean sample of kaons. The backgrounds here are dominated by other kaon production processes, plus some pileup that we have to subtract. So this is an ongoing effort. I want to talk briefly about a very puzzling result that we have on Minerva. So one of the things that we would like to do is be able to make more robust measurements of the effect of the nucleus directly. And one idea in an experiment like Minerva, where we have many different nuclear targets, by the way, T2K has something quite similar, but we have some more different nuclei. So we're able to measure events that originate in these passive nuclear targets, and to look at ratios, and that makes the uncertainty in the neutrino flux drop out. So potentially it's a very powerful tool. There are, of course, problems with this. It's passive material, so you may not have all the same access to the final state. And you want thin targets in order to avoid this problem of the passive material, but then you run into problems with statistics. Nevertheless, Minerva has made a measurement. So what's shown now is the ratio of different targets, lead, iron, and graphite to scintillator. And this is the data compared against the model. Now, that model has most of the effects that you would think of in it. It knows about the non-isoscalarity of the target. It knows about the Fermi gas. It assumes, because there's no measurement, that the effect in deep inelastic scattering would be EMC-like. Right? It would be an EMC effect like correction. But we honestly don't know why this is happening, particularly at high X. And these are events that are mostly elastic or nearly elastic events. So these are not deep inelastic scattering events. So there's some dramatic failure of this model, perhaps in the modeling of the initial state on these very heavy nuclei. We need more data in Minerva to understand why that's going on. One idea to try to do a better job of this in the future is to dress up Minerva like a seafaring captain and put the captain liquid argon experiment in front of it. That gives you the potential to do the ratio in the same beam of two very different, very capable detectors, scintillator and liquid argon. And you could get very high statistics events. This is a possibility being entertained at Fermilab to run near the end of the decade. All right. I want to mention one final experimental result before I go to my conclusion, and that's coherent pion production. So Marco already mentioned this unusual reaction where your weak boson turns into a pion in the field of the nucleus. I'll wrap it up soon. By exchanging a very small amount of momentum. So one of the things that Minerva has done and T2K is now doing is to do a reconstruction where you kinematically measure this, and then that gives you access to a model-independent measurement of such events. And if you do that, one of the things you find is that the current neutrino interaction models definitely overestimate what's going on at low pion energy. Low pion energy has the biggest effect on the cross-section at low neutrino energy. So the puzzle that Marco mentioned, where you have this suppressed, apparently at very low energy, this suppressed coherent scattering may in fact have a resolution pointed to by the Minerva data. All right, so I am out of time and the chair has kindly let me blither on for a few minutes, so I will move to my conclusion and let everybody go to the picture. So I think what I've tried to explain is that the goals of the neutrino interaction experiment that we're doing now are to improve the modeling. There's a very close correspondence with theory. It's no accident that you've heard a lot of the same parts of the story from me and from Marco as we've tried to explain the problem. And one of the things that's very exciting about this field is that there's a lot of new experimental data and even more to come in the future as we go to new facilities. So I think when we meet again in 2 years, you'll hear yet another interesting set of puzzles and perhaps resolutions. Thank you for your attention.
Thank you, Kevin. Questions for Kevin?
I can repeat the question. Yeah.
I don't know why you're surprised that in heavy nuclei the Fermi gas model does not work, because we know for years and years of studies and experiments, the correlations are so strong
Right.
that will destroy the Fermi gas model.
Yeah. So
So I think it would be good that now we try to get into this field, also the people who do nuclear structure, so that you would be able to get more reliable estimates for the cross-sections in these.
Right. So I agree completely with the question, so I'll just rephrase it briefly. The point is that we should not be surprised in any way that the Fermi gas model badly breaks down in these very heavy nuclei. And this is potentially quite a problem for argon experiments already. It's clear we need to go beyond where we are, and we should be involving more of the nuclear theory community like Marco and his collaborators. Absolutely.
Any other questions or comments? Okay, if not, thank you again. And don't run off, we have a picture to take.
So we are going to take the